Hello student, to our web optics course. Today we have lecture number 12 and today we have a very important concept we are going to learn, and which is the concept of coherence. Okay, so let me start with the basic idea that we have. So today we have lecture number 12. And today our topic is coherence, a very important topic conceptually as well as in understanding wise. Coherence. So when we have a pure monochromatic wave, then that pure monochromatic wave, it is emitting the light, and the light for that pure monochromatic wave, this is the most ideal case, that it is for pure monochromatic wave, that is a wave that is having a single frequency. That is the meaning of the monochromatic wave. Then what happened, that if it emits light, that can be represented, the light wave can be represented as this harmonic wave. The electric field, which is a function of time, over time it is moving like this. And for perfect monochromatic source, that is where the frequency is very precise. If I draw the frequency, it should be like this, and this is the frequency of this particular wave, very precise. Then we can have a infinite wave which is moving in a sinusoidal fashion. So for perfect monochromatic source, the displacement, whatever the displacement I draw here, remains sinusoidal. For t, so I should write the displacement remain sinusoidal. For a time in the limit minus infinity to plus infinity. So eventually we have a continuous flow of wave without any jump or without any phase distortion in it over the time period. This is the most ideal case, and we called it the pure monochromatic wave. However, in the actual source we don't have. So in actual source, what happened, we don't have a specific, very specific frequency, rather we have a frequency distribution. And what happened, that the electron, it goes to higher energy state and going back to lower energy state, and it emits some light. When it goes up, and which is goes up and then go down and emit some sort of light, with this time period, whatever the light it emits, it has a sinusoidal structure on that. However, there are different energy state in the source, and in different phase they are emitting light. And what happened that the radiation that is coming out is some sort of discontinuous over this phase. So this kind of discontinuity one can expect when we have the actual source. This is for actual source. So if I try to understand this with figures, with whatever the figures I draw, if I write in a nice way, then for actual source, the disturbance that is coming, so let me draw this. So suppose we have a radiation, and then there is a sudden jump of the phase, and we have a radiation. Then there is a sudden jump of the phase, we have a radiation. Then there is a sudden jump of the phase, we have a radiation. It is something like that over T. So from this to this, you can find that from here to here in this region, there is no sudden change of the phase that is marked by this vertical dotted line. Here there is a sudden jump in the phase, but in between this region where we have a almost perfectly harmonic wave without any phase distortion, we don't have any sudden jump. And this time where where we have a definite phase relationship, we can write this time as tau 0, this span of time rather. So this finite span of time where it remains sinusoidal is called the temporal coherence of, this is called the temporal coherence of the beam, this time. Or temporal coherence time. This is our temporal coherence. So what is the meaning of temporal coherence? In actual source, what happened? So the definite phase relationship exists only for finite span of time. In the previous case, when we have the purely coherent source or purely monochromatic wave, then any point if you go, and then you can predict at some point t, another point t, what should be the phase. So there is a definite phase relationship throughout the time. So the coherence time here is in general, in principle, it is infinite. However, for actual sources, what happened? The electron can goes from lower energy state to higher energy state, and it then goes back, and some radiation will happen, and it goes. This will be done in a random fashion, and as a result, for a small span of time, we have the wave that is coming from this kind of system. For a small period of time, we have a definite phase relationship of this radiation. And if I draw, as we have drawn here, that we have a span of time where we have a definite phase relationship of this radiation, and here we can see these are the jumps one can expect of actual source, because the phase relationship is not throughout the time, but there is a span of time tau 0, and where we have a phase relationship, and that time t0 or tau 0 is called the temporal coherence. Now these are the finite harmonic waves. These are the finite harmonic waves. If I want to calculate the what is the, I mean, if you for this finite harmonic wave, so let me first write it. These are the not like previous case. In actually, I mean, in pure monochromatic wave, what happened? We have a wave like structure, we have a disturbance that is moving from plus infinity to minus infinity over time. So this is an infinite harmonic wave. But here in this case, we have discrete this kind of waves which having a definite phase relationship, and this span of time we have finite harmonic waves. So if I draw this time span, let me draw it. So it is something like this. So suppose this is, so okay, my drawing is slightly, so it should be so let me let's see. So yeah, so this is my finite time. From here to here it is tau naught, and if I write this is my 0 position, so this is tau naught divided by 2, and this is tau naught divided by 2 with a negative sign. Okay, so this is the distribution we have, which is a finite harmonic wave. And if I want to write this functional form mathematically, this wave mathematically, then it is a function f of t which is having the value e to the power of minus I omega naught t, that is the expression of a harmonic wave, but it is true only for t less than t naught by 2 greater than minus t naught by 2. In this region this is true, and rest of the cases it is 0. When rest of the cases 0 means if I go beyond that, so we don't have anything. So only it is a finite harmonic wave with the time span this, like a section of these waves that is coming from the actual sources. This is a section of that. Okay, once we have that finite wave in time domain, it is possible that we can find out what is the spectrum of this finite wave. What is the meaning of the spectrum? If we have a function in time domain, then in principle we can find out what is the corresponding function in the reciprocal reciprocal domain or in the frequency domain, that is g omega. So g omega is something that one can find by making a simple Fourier transform of this finite wave. I don't know, student, whether you are aware of the Fourier transform or not, but for the time being, I'm assuming that you are aware of these things. And then let's see what happened if I do a Fourier transform. You may note that in the previous case, when I mentioned that if a wave is moving infinitely without any phase distortion, that is definite phase relationship is there, then the corresponding frequency, of these whatever the wave that is coming is a very precise one, omega. And if somebody want to describe this kind of function, this function, say suppose this frequency is omega at omega naught, that is the frequency of this radiation. Then whatever the wave we have, if I describe this as E0, E is equal to E0 e to the power of minus I omega naught t, and there is no restriction over t, it is from minus infinity to plus infinity. And if I do a Fourier transform to find out what is its corresponding frequency, then one can do the Fourier transform easily, and one should get a delta function with this form, that a particular frequency omega 0, there is a sharp peak, and then rest of the value is 0. That means we have a very precise frequency when we have a infinitely extend monochromatic wave. But for infinitely extend harmonic wave, but for finite harmonic wave, if I do the same treatment, like try to find out what is my g omega, we need to do a Fourier transform. Now the frequency spectrum one can calculate. Now we find, so here we find g omega, which is the frequency spectrum of the finite wave. For this finite wave, we want to find out g omega, how the frequency is distributed, and in order to do that we need to do a Fourier transform. So g omega is simply 1 divided by 2 pi, goes from minus infinity to infinity. That is the standard way to write the Fourier component of a given function ft, e to the power of I omega t dt. Here I should write once again what was our ft. So it was a finite wave and ranging from tau 0 by 2 to minus tau 0 by 2. This is my tau 0 equal to 0. This is the not tau 0 equal to 0, notation is not correct here. This is just the 0th location, and this is basically time t. So my function was, let me write down the function here only, that if t is equal to e to the power of I omega naught t with a negative sign, that is the way we define, for the time range this, and 0 elsewhere. In all the other point it is 0, except in this region it has a harmonic structure. Now if I put it back to the expression that we had, so g omega will be equal to 1 by 2 pi. The function is 0 all other points except this limit. So I'll put that limit. It should be minus of tau naught divided by 2, and it is tau naught divided by 2 and we have e to the power of I omega minus omega naught t dt. So that is the expression we have, and if somebody solve this simple integral, he or she will going to get like 1 divided by 2 pi, then e to the power of I omega minus omega naught t whole divided by I of omega minus omega naught, that is the integral we have with the limit minus tau naught by 2 to tau naught by 2. That is the limit we have. This is omega naught. So this value is essentially 1 divided by pi omega minus omega naught, and then e to the power I omega minus omega naught multiplied by tau by 2 minus e to the power minus I omega minus omega naught tau by 2. If I put these two limit, it is easy to show that this value is essentially sine of 2 of I of sine, and this 2 will cancel out and I will cancel out. So 2 I will cancel out. So essentially we have sine of omega minus omega naught tau naught by 2. Now if I write omega minus omega naught multiplied by tau naught by 2, a new variable say alpha, then my g alpha will be something like tau naught divided by 2 pi. One tau naught will be there because omega minus omega naught tau 0 divided by 2, that we took alpha. So here omega minus omega naught is there. So if I write entire thing in terms of alpha, it should be sine alpha whole divided by alpha. It is something like this, where alpha is defined by omega minus omega naught tau 0 divided by 2. Well, this expression suggests that this is a sinc function, because this function we know this is called the sinc function, which is defined as sin x divided by x. So here also we have a function like this, and if I plot this function, I'm going to get a structure something like this. So this is my g omega function, and here if I plot in terms of omega, then this value is 0, so that is omega 0. So around omega 0 it should have a span. So initially, if you remember, so I'm going to show side by side. So let me find out what is this value, and this value. So this value is essentially at alpha equal to pi, and this value is alpha equal to minus of pi. This is the coordinate we have. So when alpha equal to pi means this value is at omega 0 plus 2 pi divided by tau naught. If I put alpha equal to pi here, then I can find out what is the value of omega, and this value is omega naught minus 2 pi by tau 0. So we have a width here along which the function have a value, and that width, if I calculate, we call this at half width. That value is essentially delta omega is equal to 2 pi divided by tau 0. So this is the width of this spectra, and that spectra is this. So let me now tally one by one. So for infinite wave, this is infinitely extended wave, we have a frequency distribution. This is in time domain. We have, suppose we have a function f of t, doesn't have any restriction, so it is having, in frequency domain, it is having a very sharp looking function like this, and this is omega naught, and here the g omega is equal to, mathematically if I write, it should be a delta function, delta omega by minus omega naught. But here in actual case, the wave that is emitting is not finite. It is not infinite, it is finite. And if I draw that wave in between minus tau naught, sorry, this is plus to minus tau naught by 2, is something like this. So in this span, it is finite. Apart from that, in left hand side or right hand side, it is 0. So my function here, so here the functional form if t was e0 exponential of minus of I omega 0 t, but there is no restriction over t. Here the function is finite, so we have a restriction over t. So my functional form was minus I omega naught t with a restriction over t, that it is not for all the t's, but only a small span of t, which is minus tau naught divided by 2 to plus tau naught divided by 2, and 0 otherwise. As soon as we have a restriction of the function in time domain, we find the g here is having a form like this. G of omega here is proportional to a sinc kind of function. We have sine of omega minus omega naught tau naught by 2 whole divided by omega minus omega naught tau naught by 2. This is the functional form, or in other way it is sine alpha divided by alpha. But the point is, here instead of having a sharp value at omega naught, we have a span. We have a span here, and that span, if I write half width, so delta omega is a half width, and that half width we find the value. It is 2 pi divided by tau naught. Well, now it is interesting to note that if tau naught goes to infinity, what is the meaning of that? If tau naught goes to infinity, that means this finite, whatever the finite harmonic wave we have, it is no longer finite, it goes to plus infinity to minus infinity. So this reaches to the actual case. Then this delta omega, that is the width of the source, the frequency width of the source will goes to 0. So that is the relationship between these case 1 and case 2. For finite case, we have a frequency span. So the wave trend can be represented by not by a particular frequency omega naught, but some other span is there in case of finite wave trend. And in other case, when we have infinite wave trend, then the frequency will be defined very precisely as omega naught, and because of that, what happened, we have a definite phase relationship between the wave whatever the time we have. So in case 1, we have coherence length that is tends to infinity. So this is the purely coherent light. So this is the absolute coherence is there, and this is the most ideal case, which is normally not happen in the physics. However, we have more realistic case in case 2, where we have finite waves. Finite wave means the wave trend that is coming here, it is finite over time, and we have a finite harmonic waves here. And for finite harmonic waves, we find that if it is finite, and this finite thing can be quantified by this time span tau 0, which we call the coherent time. So if it is a finite coherent time, then in the source there is a frequency distribution. So omega naught is not only omega naught, it is omega naught plus pi by 2 pi divided by tau naught, and omega naught minus this side also it is minus of 2 pi. So we have a span over that. So if I quantify the half width at delta omega, so this is, so that means we have omega naught plus delta omega, omega naught minus delta omega, that is the span. So 2 of delta omega, that is the width of this span. So we have a span over frequency, and that's why we have, so we have the discrete radiation. There is no phase relationship between this harmonic wave that is radiated. So today we learn a very important concept, the concept of coherency. And what is the meaning of concept of coherency? That we find, this is a temporal coherence. We find that if we have a source, and if this source is emitting light, then there is a phase relationship one should expect for a finite span of time. After that, there will be no phase relationship, and we say that the coherency is only for that period of time. After that, the coherency destroyed. Today we don't have much time to describe more about these things. Maybe in the next class we are going to extend our discussion, and we will going to discuss how the coherency will be also considered in as a spatial, in the case of spatial distribution of the light, we call the spatial coherence, and in this case we are going to have a temporal coherence. And we also quantify in the next class to a very specific parameter called the degree of coherence. In degree of coherence, we try to understand that what happened if we have absolute coherence, then two light will interfere, and what happened if we have partial coherence, if two light interfere, what happened, and if there is no coherence at all, if two light interfere, then what happens. So we quantify the degree of coherency in a mathematical way in the next, maybe in the next class, and then things will be much more clear to you that how one can calculate the coherency, how it is related to the visibility of light if two light interfere to each other. And if I want to find out the fringe, then a particular pattern we call the interference pattern, we will going to discuss these things in the next few classes. Then coherency is a very, very important property that one should have to find a very distinct fringe, and why it is coming, what is the background mathematics, what is the background physics of that, we are going to discuss in detail. With that note, I like to conclude today's class. Thank you very much for your attention, and see you in the next class.